from our growing up is like, who designed this kind of thing? You know, if you have to work on it, you design it differently and you maintain it differently as a result. So really keen to provide that type of an applied approach to the work that we do, whether it's design work or the field testing that we provide. Now, just a little bit of we've talked a lot about agrology and things. I'm going to get this out to the engineers in the crowd and make sure that we can talk a little bit about what we do for our process. It involves design and verification as one aspect. So verification is, did I meet the requirements that I intended to do with my piece of equipment? That's one aspect of what we do. The second step going up the slide is validation. So did it actually meet and perform as intended for the end user? So 2 steps in the process. We work very closely with our teams that we deal with on manufacturers to provide that breakdown and really systematic approach to take these requirements, work on a very small level, and build up from there. So making sure that at the end, if we're looking at, say, equipment such as technologies and sectional control, you use the various steps at a very discrete level, and you build up from there to get the end product to make sure that your requirements at the end are actually going to be in practice when you get to the field. A little bit of background before we actually get into the sectional control study in terms of what the results were and why it's important. So we did a study as a background in 2006 with these parties, and it was to understand what the implications are and what the standard would be if you look at overlap as a whole and bringing the impact to a value and a number that can be assigned to producers for their type of practices. Really, you look at one of those things of why it's important, well, inefficiency and waste. If you don't double up on anything, then it makes it more efficient, and it goes across the spectrum. We'll look specifically at the front end process in terms of putting seed in the ground and what that means. One aspect I'll say just in terms of this, when you're looking at other conversations about GHG or carbon, that's usually a result of efficiency. So we really want to focus on efficiency. If I'm efficient, I'm also 9 times out of 10 also greenhouse gas or carbon friendly as well. So there's a twofold benefit for looking at efficiencies as part of the overall spectrum. I want to take a big picture approach to these things too, not just look at it on a particular small level, but look at it as an entire system. What practices, what equipment do I use, and then how do I use them in terms of the overall impact for developing the type of work that we're trying to accomplish at the end. Now, again, I'm sure most of the people in the crowd are going to say, but we'll just put this in context. Headlands being one of those overlaps we're going to look at, but also obstacle overlap. Those are the 2 things in terms of what we tested, we're looking at to try and accomplish and put in context overall. Now, when you look at overlap, what does that mean? There's a theoretical overlap, which is, again, best case scenario. If we could never overlap, this is what it would look like based on acceptable practices. Reality is, nothing works exactly as you want in theory. There's always some limitations, and that's a practical side of it. So, you know, that's the aspect you need to keep in mind, is the best case scenario versus a reality, and trying to minimize that, and that gets you to the end goal of reducing and providing a solution that works. Now, how do you deal with the overlap? Well, there's a couple things that come into play. It really depends a little bit in terms of the obstacles in the field. And those are some of the situations that you have to account for in terms of the overlap, whether it's an obstacle that's evenly shaped, round, or if you get into an oblong or different kind of shape. And there's a sensitivity analysis that goes with that. We wanted to look at and evaluate these different types of variables for overlap efficiency: field size, terrain overlap, obstacles, and the technologies that can go with that when you put this in terms of context for studying. And when we looked at this, I'm just going back one, looked at 64 different fields as part of that initial study to understand what's the overall overlap that varies and goes with the different types of fields that we're providing, whether it's seeding, spraying, or fertilizer, and then implement sizes as well. You know, anywhere from 33 feet up to 100-foot wide sprayer. What does that look like in terms of overlap? This is what we found when we did our initial study. Field size was one of those types of variables that can have a dramatic impact, and as you get larger in size, opportunities for efficiency increase. and it goes to reason that there's less overlap. So one of those things as you get into those obstacles and things that deal with the potential is that much greater for overlap compared to larger fields. Other aspect is, okay, we're breaking the field up. What does that do for your risk or your potential for overlap? Higher probability if you have more than 5 obstacles inside a field. Now it's pushing like 9% overlap potential. When you look at edge obstacles, again, the variability that goes with not having a perfectly square field, those are things that influence and impact what your overlap potential could be, as well as things such as ditch or creeks, which are those things that can cut through on a very unique or random type of a process and irregular shaped boundaries that can impact the overall overlap potential. When we look at the implement size, there's that theoretical versus practical. We did some work looking at modeling, and we took different pieces of equipment and different widths and looked at what's that practical overlap versus the theoretical. And again, no surprise, as you get larger, those things can increase. And when you look at the practical overlap, 7% as you're getting over 60 feet. So those are things that we look at. I want to put that in context in terms of what our study was as we got into the overall evaluation and field testing of sectional control as part of our project. One other thing that we looked at with management agriculture is obstacle consolidation, water. That's one thing that we could look at and combine and say, hey, if we can take all of our depressions and put them into one spot, we want to maintain our overall total water volume for conservation reasons and manage it differently. What does that do? And one thing that we did find was, well, yeah, that's definitely an option. You can reduce the amount of water from an area of 9.6 to 5.3 acres. Big difference if you can reduce, again, when you go back to the obstacles, number of obstacles and potential for impact. Now, if you can't do that, though, then you start looking at the next phase in terms of managing situations and ways to take care of what you're trying to manage and reduce overlap. And that's where you get into sectional control. The sectional control study was really to evaluate the emissions reductions and cost savings with air seeders, drills, and sowing equipment. Want to say thanks to, first of all, our project funders and partners as listed here, Canadian Ag Partnership, as well as the Alberta Pulse Corps for funding the project, along with our partners in this particular project. PAMI's role in this was to look at field testing, the different types of equipment, as well as the obstacles that go with using sectional control technologies. We looked at a 90-degree to the headland, as well as obstacles as one of the things to study and understand what does that impact on overlap potential. Equipment type ranged from a 80-foot unit to 100-foot, again broken down into various number of sections, which results in a certain section width. So that really defines how large your overall equipment width will be. Going back to our initial study, we know that smaller sections mean potential for lower overlap as well. But what does it look like in real life and practice? And when you look at operator preferences and equipment settings, such as the look ahead and look behind times, those are all parts of the overall process that are used. We used the equipment as our operators were running them. We weren't looking to modify or optimize necessarily these particular settings. It was as a technology as a whole, how does this look like when it gets into the end user's hands? How do they use it and implement it? And what kind of overlap could you see as a result? And we also looked at two different types of seed, one being pea, being a large seed size, and the other spectrum being canola, being a small seed size, but lots of fertilizer going down, and that pneumatic conveying system. What does that do for your overlap potential and the results thereof that go with it? So we looked at ground truthing, the actual overlaps. We had our people in the field on those three different pieces of equipment, and we compared our infield measurements then, counting plants, looking at the area that we saw overlap compared to what the theoretical was when you look at your monitor, and going through that process to understand what's that overall aggregate of information looking like. So we didn't break out the individual technologies intentionally. It's intended to provide that overall assessment and implementation of a technology across brands, colors, makes, and that's part of the process we want to understand is what is that being used as and how is it being implemented by producers and perform at the very end. The second aspect, and this is one really key part, was understanding the units that can lift the openers and the draft load that can go with that. Two aspects. One is the emissions reduction potential from reducing that overall load on a particular piece of equipment, and then the calculated power savings that go with that. And to show you, we have put a calibrated load cell in between the tractor and with this little load cart that we call it, and we allowed us to go and measure the overall amount of force that the towed implement is seen and being applied. And we went through a process of lifting individual sections to understand, as we were lifting them, what does that sequence do for going from side to side, just to make sure we had a straight draft load on that implement, and what was the impact on overall draft and emissions reduction potential. Trying to keep a standardized process always is one of those keys, and we used about a quarter-mile stretch again to make sure that you get stabilized, account for variability in a field, and give a good data set with reduced variation as much as possible. And from that, you can calculate your overall power that would be saved as a result. Here's the results. So what do we find? And we start looking at the data. How do you break this down into something that you can look at and use? So we looked at it on their different widths, and decided and looking at the data and realized that we needed to normalize the data set and bring it into a per square or per foot implement width. And when we saw the data canola, we had about 16.8 square feet of overlap when we're looking at our overall potential when you're looking at obstacles. And on the headlands, not surprisingly, is a bit higher at 21 square foot per implement width when you're looking at that overlap potential for the individual units. Now, if you take that on a per width basis, you got to extrapolate that. What does that look like now when you put in on a quarter section field, and the number of obstacles as we're looking at as means to say, hey, does this technology improve, or what does it look like theoretically compared to the overall potential? And I'll say one of the things we did look at, and across the bottom you'll see, is you increase the number of obstacles. That sectional control does provide that type of savings that you're looking for, and it's fairly consistent. So increasing number of obstacles doesn't have the same kind of dramatic effect. The technology works in order to reduce the overlap based on the results that we saw with our people in the field when they're counting plants in the area that we saw on the overlap side. Again, never going to be zero, but what's the lowest that we can get to, and understanding those kinds of implications for the overall process for seeding tools. Looking at peas, again, different type of process, seeds bigger, different airflows, and understanding what the implications are for that. We saw 16 square foot per implement width on an obstacle, then on the headlands 14.4. So a little bit different in terms of what the overlap potential was, or what the overlap was measured when we're looking at the two different types of overlap, whether it was an obstacle or a headland. Now, one of our hypotheses was, it's the fan speed that's making some of the difference when you're looking at the seed distribution in air seeder. Haven't gone through and had that step validated, but that was just something as we're looking at what's the difference between peas and canola. That's one thing to consider, is fan speed, and how that look forward and look behind times impact your distribution system and has the amount of seed that goes into the ground at the time. Again, looking at the overall results, P, because it's slightly lower, when you put that into context of a larger field, slightly lower across the board for the overall number of acres that you'd see and the amount of overlap percentage-wise on implements ranging from 60 to 100 feet. Again, the technology is working, it's doing the job that it should. A little bit different when you're looking at the different commodities, but again, each seed is different, and the specifics of that are one of the things that are important to consider with any kind of technology. Now, one of the other parts that we wanted to understand was what we monitored in the cab versus what we saw in the field. And as you can see, the overlap being doubled up, and then any skips we'd see as white sections on a headland pass and as all swell on an angle. One thing that we did notice in the field was, you didn't see that kind of miss. That was very rare, and it's not necessarily as much of an issue as one would think if you're sitting looking at your monitor. So it's, I'll say, a little bit optimistic maybe in terms of what is happening in the field, but a good news story when you consider the overall impact of having a miss in a field. One other aspect is we wanted to just understand a bit more in terms of what is that obstacle compared from the actual versus what we're seeing on the monitor compared to when you look at from going towards the headland versus going away. Also, when you look at an obstacle again, what does that mean in terms of which direction I'm going? Does that have an impact overall in terms of the overlap that you're seeing on either a 60-foot implement as well as on a 100-foot implement? Some really interesting results, not something that I was necessarily expecting to see necessarily, that the direction does matter with some of the things that you're looking to understand to do with both the peas and the canola. So again, some really interesting results, and that's part of what I enjoy with these kinds of projects, is getting to get into the field, understand what technology is doing, and some of these unique things that come out of any kind of a data set that comes from being in the field, understanding what the overall process is and can be in terms of the technology and how it uses and how it's been implemented by producers. One of the last parts to this was looking at the draft reduction in terms of as openers lift for your sections. I was expecting, I'll say, when we're looking at the line on this chart in terms of the percent of the implement in the ground. So at the bottom, that's the fully lifted compared to as you take one section out of the ground. We're expecting to see a fairly linear curve. Didn't necessarily see that. So there is some interesting aspects in terms of as sections are being in the ground, the additional side load going on potentially, and you're getting some side load effect, not a straight draft pull, which can impact your overall draft force that the tractor is seeing on that. Just a little bit of note on that in terms of how this was implemented and the testing that was done, and the knives and the equipment configuration that was used for that. Just a 5 mile per hour ground speed was the overall speed that was targeted, and again, looking at the impact on that and trying to manage and minimize any kind of overall impact for the operation. Soil type 2, just want to make a note of that. That was in a loamy soil, and did soil test to confirm and make sure that we understood some of the context and the variables that we had in place at the time as part of that. And moisture content was in that 16 to 24% range in soil. So again, trying to find that combination of factors, parameters that make a difference in understanding and developing a process that works for overall production and making a difference for openers. I guess just in conclusion, really understanding your equipment and settings is one of those key parts of the overall process, and anything that you're doing, any kind of equipment, that's a really key, whether it's a combine, air seeder, you got to know your machine, you got to know the variables that you need to invest some time in to set up and optimize very well. You got to validate too, the next step, take some measurements, make sure that you're getting the performance that you're expecting to see in terms of the overall potential or risk reduction that you want to accomplish from any type of process, any type of machine. Just a real key part of the process for doing equipment setup. And the last thing I'll make is sectional control does work, and we saw it with our results based on the ground truthing that we did, getting our shadow into the field and testing and validating the overall process as well as a theoretical compared to the end of the row. So just with that, I want to say thank you, and here's my contact information if anybody wants to look me up. This information and the report on the sectional control is available on Team Alberta's website. So if you're looking for that link, by all means, just look up. You'll find that there, and available. Full report's available for download if needed. So thank you.